So we are going to study the UV spectra. So UV spectra, we have to learn a few examples. The spectras of the first one is the spectra of acetone, and acetone we know that it is CH3CO CH3, and whether it is aldehydes or ketones, it will be having a carbonyl group, that is C double bond O group. So since the carbonyl group is present, that is we have a double bond. Double bond means it will be having pi electrons, and since the oxygen has got two pair of lone pair electrons, and therefore we can say that it will be having non-bonding electrons. So all aldehydes and ketones, since it is having a carbonyl group, we can say that it will be having the pi electrons and also the n electrons. Okay, so in the case of acetone, you can expect N to sigma star transition and pi to pi star transition and N to pi star transition. And in this case, we can say N to sigma star transition is found to be between 150 to 160 nanometers, and pi to pi star is found to be between 180 to 190 nanometers, and that of N to pi star is found to be around 270 to 295 nanometers. And we can say that there is a change in their readings. Okay, we have written a range. So this range is written because depending upon the medium or depending upon the solvent, you will be getting the exact absorption spectra. Okay, now we'll see how you can plot, or in this case you can say that 150 to 160 nanometers and 180 to 190 nanometers, both these are coming less than, okay, these are found to be less than 200 nanometers, and it is not possible for the UV spectra or UV spectrophotometer to read these two readings. These ranges cannot be read, that is because it is less than 200 nanometers. So in the spectra you will be able to see only this range, that is from 270 to 295 nanometers. Okay, and then we can say that you can plot the graph between epsilon and lambda. Epsilon is the energy that we have already studied, and then we have the wavelength. Now here I have plotted two graphs. One is the graph of acetone when the solvent is water, and at that time we can say that the epsilon lambda max is found to be 264 nanometers. And in the case of acetone in hexane, okay, hexane is used as a solvent. Okay, when hexane is used as a solvent, we can say that the spectra of acetone will be in this way, that is you will be getting the lambda max at 279 nanometers. Okay, so this is the spectra of acetone in water, solvent water, and also in solvent hexane. Now we will see why there is a shift. Okay, water means it is a protic solvent, whereas hexane is an aprotic solvent. So protic solvents means lambda maximum will be shifting to the lower wavelength. Okay, in the presence of protic solvents, we can say that the lambda max will be moving to the lower wavelength, because in that case we can say that there is a hydrogen bond formation, because water, we can say, okay, water is a solvent here. So we have the water and then the carbonyl group, so there can be a hydrogen bond between this oxygen and this hydrogen. So since the hydrogen bonding is there, when the hydrogen bonding is present, means the lambda max will be decreasing. So in the case of water solvent, we can say acetone will be having a lower lambda max. Okay, and in the case of hexane, it is aprotic, there is no hydrogen bond possible in this case. So we can say that there is no reduction in the lambda max. Okay, when the lambda max is reducing means their energy will be higher, and that is why we have lambda for this lambda max. For the acetone in water, it has got higher energy than that of the acetone in hexane. Okay, so this is all about the UV spectra of acetone, and the question will be coming as such, and you are supposed to write only what is required.